Hey guys, good morning. So everybody's there. Wow, nice. I'm only late. Okay, cool. So we'll start right away. We will share my screen. Okay, so we have almost completed all types of reactions, eliminations, addition reactions, everything we completed. So I just want to talk about your nucleophilic substitution, right? And electrophilic substitution. There is only one type of reactions left, that is substitution, right? So substitution again can be either nucleophilic substitution or electrophilic substitution, right? So okay, so when I say substitution, right? So substitution, you know what is going to happen? I'm going to replace one group with another group, right? So as I told you, it can be of two types. One is nucleophilic, another one is electrophilic, right? So you understand what is going to happen here. Here I'm going to replace a negative charge with another negative charge, and here I'm going to replace a positive charge with another positive charge. That is what is going to happen, right? Okay, so we'll talk about first nucleophilic substitution, right? We already know so much about it. SN1, SN2, all these things I've already studied, but I'll just give you the details, the details which you don't know, right? Okay, so common. If I write a general reaction for any nucleophilic substitution, say I have RLG plus the incoming nucleophile, right? Will give me R nucleophile and the leaving group leaves, correct? And the leaving group leaves. That's what you need to understand, right? So now the LG represents leaving group. We already mentioned it, right? Okay. So now the question is, guys, it's like a displacement reaction, isn't it? Normal, I have a single displacement reaction where I have one cation or one anion replacing the other one in the salt, right? So obviously, what you understand is, say for example, if I put copper plus HCl, now tell me whether this reaction will happen or not. If I put copper plus HCl, will this reaction happen or not? I would say not copper. I just, okay, maybe, yes, we can do this. Will this happen? Will this reaction happen?
So no, it won't.
Yeah, right. So why? Because copper is less reactive than hydrogen. Hydrogen is more reactive than copper. That means copper cannot replace hydrogen from its compound, right? So basically, it all depends on the reactivity, right? So here also, people, here also in this nucleophilic substitution, you are going to depend upon the reactivities, but we are not going to call it as reactivities. I'm going to give you some technical name, right? So that particular term which we are looking into is this term. It's called this one, nucleophilicity, right? So basically nucleophilicity, I would say it's a kinetic term, right? It's all about how fast a nucleophile can go and attack the substrate. That's all about it is, Okay, so when I say nucleophilicity, I'm talking about the reactivity of the nucleophile. So it's not going to depend on this. No, it's not going to depend on the substrate. It is just this nucleophile, right? This nucleophile, this nucleophilicity. Okay, so it's going to I will define it as how fast or what is the ability is of the nucleophile to go and attack the substrate. How fast it attacks. That is what is nucleophilicity, right? Now, can we determine it? If I give you two nucleophiles, say if I give you OH minus and Cl minus, or say Cn minus, H2O, you know, so many nucleophiles. Now, if I give you all these nucleophiles, will you be able to predict which one is more nucleophilic or which one is less nucleophilic? All these things, will I be able to predict? Yes, there will be able to predict. There are certain ways by which you'll be able to predict. Okay, so what are the ways by which I'll be able to predict the nucleophilicity? There are a few points you can follow, right? So the first point in which the nucleophilicity is going to depend on is about the basic strength of the nucleophile, right? Basic strength of the nucleophile. Now, we know what are Lewis bases. Now, tell me what are Lewis bases, people. What do you mean by Lewis bases?
Ability to donate a pair of electrons.
Exactly. Correct. So it's the ability of the particular substance or species to donate a lone pair of electron, right? So that's what is basically Lewis base, right? So we need to have a basically like something like this, a base with a lone pair, right? Is that what that's what we are looking at, right? Now, obviously, what you can understand is, so you can see that the nucleophile is here is carrying a negative charge, right? And obviously, it is going to attack the R or the substrate or whatever you want to call it, right? Something happened. What happened? Okay. Anyways, right? So you're actually seeing that this nucleophile is actually acting as a base. Is it not? Obviously, there'll be lone pairs present on the nucleophile, right? And okay, so obviously there'll be lone pairs present on this nucleophile, right? And that is obviously only going to attack the substrate. You can see it's not actually the negative charge. It's actually the lone pair of electron which is actually going to attack the substrate, right? So what I can say from this is that uh, see, but there is you can understand that there is actually going to be some difference between your nucleophilicity and basic strength. Like even though you see that almost they're similar, right? They're not exactly same. Now, why I'll tell you is because basic strength is a thermodynamic property in the sense that say if I have a base B minus, or say whatever, if I have a base, right, and if I have an acid, say HA, right? Now, obviously, I'm going to form AB plus H2O, like I'm going to form a neutralization reaction, isn't it? So this reaction, how much it goes on to completion, right? If I say it's 70% completed or 80% completed, obviously more and more is the percentage of completion. More and more is the basic strength, that basic strength of this base. That's how I call it, right? So, or I can even say that if I have BOH, right, now it is going to undergo dissociation to form B plus OH minus, right? So again, how much this reaction goes to completion is what is my basic strength. How much more and more is the percentage completion, more and more is my basic strength, right? So what I can try and tell you is that it is a thermodynamic term, right? Basic strength is a thermodynamic term, but nucleophilicity is a kinetic term, right, guys? Like when you go to higher levels of chemistry, right, you will actually see these two things: thermodynamic control and kinetic control. Thermodynamic control, basically you're going to talk about the stabilities of this thing. Basically we whatever we are doing here, like now we are not actually not going to concentrate on kinetic control in any of the reactions which we'll see, right? So basically when I say thermodynamic control, whichever is the thermodynamically more stable product, that is what we are going to get as the major product. Hope you understand what I'm trying to say, right? Thermodynamically, whichever is the more stable product, that we are going to get as a major product, right? That is thermodynamic control. If you want to talk about kinetic control, right, whichever product is able to form quicker, that will be the major product. it need or it may or might not, I mean, it may or may not be more stable. Hope you understand the difference, right? It's all about the time with respect to kinetic control, but it's all about stability when it comes to thermodynamic control. Anyways, we're not going into details. So what I'm trying to tell you is that basic strength is actually a thermodynamic term and nucleophilicity is a kinetic term. That's what you need to understand. But what I can say for sure is that this is definitely directly proportional to the nucleophilicity. That is for sure. Obviously, right? More and more is the basic strength, right? More and more is the ability of this base to donate the lone pair, right? And obviously, more and more will be the nucleophilicity, right? So if I take some examples, maybe it'll get you a clear idea. If I take an example, say, let me take. See, okay, let me take this thing itself. Say you have normal nucleophiles of halides. Say I have F minus, uh, Cl minus, Br minus, and I minus. Okay, now I want to decide which of them would be better nucleophile. I mean, I want to arrange them in the order of nucleophilicity. Okay, right. Now, how are we going to do it? Either we are going to use the only thing which we know right now, that is your basic strength. If I use that, we'll see. Now, tell me, guys, out of these four, which is the strongest base? Just a guess. You might not know the real reason about it, but still, what would be your guess? Which is the strongest base?
Br minus.
Br minus. Okay, guys, let me take a vote. I have four nucleophiles here. Tell me your this thing. Already one is there. F. Okay, Harish says F minus one. Okay, and another F minus. Okay, fine. Anyway, everybody participate, please. Just tell me what do you think is the best nucleophile or the most basic among all these four. I got two answers. One for F minus, another for Br minus. Okay, another F minus. I think I got almost like 4 or 5 answers. I almost have 8, 9 people here. Come on, quick, guys. I know it's morning. I know now only you woke up, but still. Even I did the same. Right? And if you know me personally, it is more difficult for you, I mean, difficult for me than it is for you. Okay, anyways, right. So now how do we go about it? Okay, so we cannot directly determine the basic strength, right? Now, what I can use is the concept of conjugates. Okay, now hope you know there is something called as conjugate base of an acid, or say conjugate acid of a base, right? Hope you remember. Have you ever heard these terms, people? Conjugate acid, conjugate base. Have you ever heard about it? I think we did, right? Obviously, we just
Yes,
did.
yes.
Right, we did this thing. Acidic strength, basic strength. We did, right? I told you that if the conjugate base of an acid is stable, then it's a better acid. Right now, there is one more thing also. You can know people. If I would say, if I talk about an acid or a base, anything, right? So the strength, right? The strength of an acid or the base is inversely related to the strength of the conjugate. Strength of the conjugates. Right? So that's what you understand. For example, if I have a strong acid, for example, right? If I have a strong acid, the conjugate base of that strong acid will be a weak base. Right? If the acid is strong, conjugate base is weak. Or if the conjugate base is strong, the acid is weak. It's vice versa. Same goes with the base also. Right? So you can determine the strength of the acid or the base with this. Right? Always the strength of a particular acid or the base is inversely related to the strength of its conjugates. In the sense that if I have a strong acid, you'll always have a weak conjugate base. That's how it works. Okay, so what I can do for this particular case, if you ask me, right? Now let me write, these would have been the conjugate bases, is it not? Right? You know what are conjugate bases. After removing H plus, whatever is remaining is what are these? right? So let me look into what are all the actual acids it would have been for all these four conjugate bases. It's simple, right? I just have to add H plus. So it would have been actually HF, right? HCl, HBr, and HI. These would have been the acids. Correct? Right? Now tell me, guys, among these four acids, obviously you would have done your P block now. You should be able to answer this. Which among these is the strongest acid?
HI.
HF. Okay. Someone say
HI.
HF.
HI,
HI.
sir.
Okay. Okay, fine. So the answer is HI. Is it not? The HI is the strongest acid here. Now, how do you predict it? It's all about the bond strength, is it not? I have this A bond, for example. Obviously, you need to break this bond for H plus to come out, right? Obviously, wherever I'm going to have the least bond strength, there only I'm going to have maximum amount of this H plus coming out, right? Obviously, I know HF bond is very strong, right? And HI bond is the weakest bond here. So obviously, if I look at the strength of the acid, this would have been the order of strength of the acid. That means the strongest acid here is HI, right? And the weakest acid here is HF. Now, when I go for the conjugate basis of these, it would have been exactly opposite. That means HI is the strongest acid. So I minus will be the weakest base. Same way, HF is the weakest acid. So F minus would have been the strongest base. Okay, so obviously, if I look into the order of basic strength of these nucleophiles, it is going to be exactly opposite of this acidic strength order. That means F minus is a better nuclear. I would say. Now first we'll talk about the basic strength. F minus is a better base than Cl minus, than Br minus, and the least basic is I minus, right? And obviously that is what is going to be the order of the nucleophilicity. F minus is a better nucleophile than Cl minus, than Br minus, than I minus. So most of your answers are correct. Yes, F minus is the best nucleophile among these four, right? Hope you understand how. Now I can actually give you one more reason for this. Not like not based on basic strength, but for these four, right? Actually, I can give you one more reason. The reason would be in the case of this thing, ionic mobilities. Mobility in the sense the ability of the ion to move, right? So obviously, an ion which moves faster, right, will be a better nucleophile, because I told you nucleophilicity is a kinetic term. It's all about how fast the nucleophile goes and attacks the substrate, isn't it? So obviously, whichever ion has higher mobility, or in the sense that whichever is able to move freely, right, that is actually going to become a better nucleophile. And again, the same order you will get, because F minus is the smallest anion, I minus is so big and heavy, right? So obviously, F minus can move faster, obviously, than Cl minus, than Br minus, than I minus. So either way, either you look into terms of strength of the base, or in terms of ionic mobilities, you will get the same answer, right? F minus is the better nucleophile, and the I minus is the least nucleophilic among all these four, right? Okay, now guys, there are certain exceptions to this. Particularly, I told you this basic strength is directly proportional to nucleophilicity. There can be exceptions to this. Okay, now let me get into it. How do we go about it? Say, for example, um, okay, say for example, if you have H2, wait. A good example I should give you. Okay, fine. Like not exactly fine. Anyways, I can give you this. Say if you have R, actually a good example only. Good example. Let's come. So I have RS minus and say RO minus. Okay, so basically RS minus is thiol, right? RS minus is also a nucleophile, right? This is alkoxide, this is sulfoxide ion. Anyways, right? RS minus comes from RSH, thiols. RO minus comes from ROH, alcohols. Okay, so now if you look into it, right? If you look into the basic strength, right? So I would say that RO minus is a better base, right? That means RO minus should have been the better nucleophile. right? But what I see in reality is, guys, RS minus is actually a better nucleophile than RO minus. That's what I see in experimental conditions. Okay, again I repeat, RO minus is a better base. Now again, why? If you ask me, you can go for the same conjugate concept. I have ROH, RSH, right? So definitely RH is a better acid. Okay, if you want, guys, I have RSH, or you can even see that just that it's I have, right, I have the SH bond, I have a OH bond, obviously, which is easier to break. SH bond is easier to break. So this would have been a better acid, right? So this would have been a stronger conjugate base. So either way, like you can understand this, right? Like this is our thiols are better acids than alcohols because of the bond strength, same reasons, right? But so definitely RO minus will be a better base than RS minus. So what I expect that RO minus to be a better nucleophile than RS minus, right? But what I see in reality is opposite. Anybody wants to come up with a reason for this? Why do I see this mismatch? RS minus being a better, even though RO minus is like basic strength is correct. Basic strength order, RO minus is a better base than RS minus, no doubt about it. But when I go for nucleophilicity, that time RS minus overtakes. Anybody wants to give me a reason of this? Why it happens like this?
Sir, something about the size of the atom?
Mm, yeah, indirectly, yes. But I want something specific. Any other answers? Okay, if size, obviously oxygen is smaller size, sulfur is little larger. So what is going to happen because of that? Don't tell me that RS minus is okay. If you bring size into the picture, RS minus is little big, so it must move slower. But no, that don't go that way, because the size difference between these two is not going to be much. Okay, talking if you talk about the atomic size of sulfur and oxygen, oh yeah, that it has something to do with this. Any guesses? Oh, there is one in the chat. Easier bond breaking. We already broke the bond, kana. Like RS minus, I mean, the SH bond is already broken. OH bond is also already broken, and that these two are going to attack the nuclear substrate. There's there's no more bond breakage here, right? So let me give you the answer. Anybody wants to? I'll give you maybe 10 more seconds. Anybody wants to give me an answer? Okay,
Sir,
then
is it concerned
yes.
with stability?
No, Kana. Okay, so the answer is it's all about the electronegativity of these two, right? So I have sulfur, I have oxygen. Obviously, oxygen is more electronegative, right? So what is going to happen because of that? Both of them have some lone pairs in them, right? So now it's all about ability of this lone pair to get donated, isn't it? Now oxygen being more electronegative, it is going to hold on to its lone pair stronger, and sulfur being less electronegative is okay with giving the lone pair to the substrate. That's the main reason. Hope you understand what I'm telling. Again, I repeat if you want. So the thing is, oxygen is more electronegative, so it will hold on to its electron pair strongly. But in the case of sulfur, little less electronegative, so it is more prone to donate the lone pair to the substrate, and that is the reason why you see this RS minus being a better nuke, even though RO minus is a better base. I see that RS minus is a better nucleophile than RO minus. Okay, there are a lot of things like this, people. A lot of exemptions you will see, right? But again, mostly it will be concerning only with oxygen and sulfur. Anyways, we'll do some problems in the when we do it, right? So this is one assumption. Okay, right. So the first criteria is over. The first criteria is this basic strength, right? Now next criteria, second point for deciding nucleophilicity. Right. So the second point for nucleophilicity is about the charge. Right? What I'm trying to say is that if I have a charged nucleophile and a neutral nucleophile, definitely a charged nucleophile is going to be a better nucleophile. That's what I'm telling you. Like, see, OH minus and H2O are going to give me the same product, alcohols in general, isn't it? If I have an RCl and if I put NaOH or say H2O, right? So you will see that both of them will give me alcohol. But if you put NaOH, the reaction seems to be faster than if you put H2O. Now, for obvious reasons, because charged species will be obviously already unstable, so they'll be more reactive. That's how you put it, right? So whenever you have a charged species, always and always and always, it is going to be a better nucleophile than a neutral species, neutral nucleophile. Okay, so that is the second criteria. Now this is a simple one. Third one is your bulkiness. Okay, bear with it, guys. My handwriting. Okay, so the third one is bulkiness. Obviously, now say if I give you an example like this, okay, something like C. CH3O minus with say um, O minus. Now both are alkoxides, right? But you see, this is very less bulky. This is so much bulky. So definitely this would have been a better nucleophile than this one, right? Okay, so bulkiness I would say is inversely related to the nucleophilicity. Obviously, now this is pretty logical, isn't it? A smaller nucleophile or say a lesser bulky nucleophile will tend to move faster. Not go attack a substrate faster. So better nucleophile. Okay, so that is the third criteria. And I would say a fourth criteria. Right. So fourth criteria is I would say electron withdrawing groups or electron withdrawing groups presence, or I would say electron withdrawing or electron donating group for that matter. Right. So okay, how would I give you an example? Okay, something like this. Say if I have CH3O minus with say CH2Cl O minus. Okay, guys. Now predict which is the, okay, if I call it as 1 and 2, which do you think is a better nucleophile? One or two?
Second one.
Second one. Okay, fine. One answer for second. Anybody wants to object or even say, yeah, that is correct? Is there anything in the chat? No. There is. 2 again. Okay. I don't know why you're telling 2. Anybody wants to come up with the reason? Why did he tell 2? Or it was just a guess?
Sir, in second one, there's an electron withdrawing group which increases
Okay.
the charge on oxygen.
Ooh, that's, if I have an electron withdrawing group, what is it going to do? Think and tell
It
me.
increases.
See, I have a negative charge on oxygen. Yes. And you actually said, yes, chlorine is an electron withdrawing group, right? So if chlorine is an electron withdrawing group, what will happen to the negative charge? Will it increase or decrease?
Oh, sorry, sir. It's going to decrease.
Exactly, right. So if I have an electron withdrawing group, the amount of negative charge is going to decrease, is it not? The electron pair is going to come towards this, right? So the amount of negative charge on oxygen in this case is decreased because of I have an electron withdrawing group. So obviously lesser charge, lesser nucleophilicity. So the first one is a better nucleophile than the second one. Hope you understand what I'm trying to say. It's pretty simple. right? So I have an electron withdrawing group, which is going to decrease the negative charge on oxygen, right? So thereby the nucleophilicity is decreased. That's it, as simple as that, right? So generally, electron withdrawing group decreases the nucleophilicity, electron donating groups increases the nucleophilicity. That's how it works. You can remember it this way, or you don't have to remember anything. Just go by logic. Okay, so electron withdrawing groups obviously decreases the negative charge, decreases the nucleophilicity, and vice versa for your electron donating groups. Is that okay? Right. Say for example, if I've given you one more thing, say if I have given you CH3, CH2, O minus, right? So definitely in this case, this would have been, I would say, this would have been the best nucleophile because I have an electron donating group here. CH3 to be an electron donating group, right? Okay. So I hope this is pretty logical. Done. That's the fourth criteria. Now moving on. Right. So the next one. Right. Now the next one is going to depend upon the solvent. Did I miss anything else among this? Yeah, nothing else. Right. So the last one, actually, this is the last criteria for us to look into it. Right. So the last criteria is about the presence of polar solvents. I would say not even polar solvents, polar protic solvents. I'll not call it as polar solvents, but I'll call it as protic solvents. Okay. Now, if you're wondering what are these protic solvents, anything which even has the slightest ability to give me little amount of H plus. I'd say even water comes into this. Even though you tell me, sir, no, does not give me H plus. No, you have. If I go to equilibrium, I'll prove it to you that it has some amount of H plus concentration. Anyways, right? So whenever you have, or I would say anything which has a bond with a hydrogen, right, and which is highly polar, which is going to have a partial positive on hydrogen and a partial negative on the other atom. So anything which has this, right, is going to be called as a protic solvent. Okay, so now in the presence of protic solvents, people, there is going to be some amazing things happening. The amazing thing is nothing but, anybody wants to guess? One phenomena is going to happen if I have protic solvents. Anybody wants to guess?
Something gets protonated.
Phenomena. If I have a nucleophile dissolved, I mean, I would say if I have a nucleophile in these solvents, protic solvents, I would say water, right? Now, what do you expect to happen? That so there's something which will happen.
Oh, intermolecular hydrogen bonding.
Exactly, right. So that's what is going to happen. I am going to have hydrogen bonding happening, right? So because of hydrogen bonding, there will definitely be some differences in the nucleophilicity between what you expect and what you see in reality. There is actually going to be a difference between those two because of hydrogen bonding. Okay, so we'll see how it happens. Now we will take the same 4 examples, people. I will just take the same 4 examples which we already took. F minus, Cl minus, Br minus, right, and I minus. Okay, right. Now we already decided now. Okay, that particular case we did it in a aprotic solvent, like whatever the case which we did here, just based on basic strength. Where is it? So we decided this is what would have been the order of nucleophilicity. This happens in a aprotic solvent. Please remember that. Okay, now if I have a protic solvent like water, as you said, yes, definitely I am going to have hydrogen bonding. Okay, now think and tell me, guys, among these 4, right, where do you think, or which anion do you think is going to involve in more extensive hydrogen bonding with water? I'll repeat the question. Out of these 4 anions, which do you think will have more extensive hydrogen bonding with water, or I would say which ion will undergo more hydration? Hope you know what is hydration. Hydration is crowding of the water molecule surrounding the cation or anion, for that matter. Here I have only anions, right? So basically hydration, yeah, definitely, right? So definitely fluorine is the one which will undergo extensive hydration. 2 reasons. right? One reason is about the size, is it not? Now I have you can easily see I have a smaller anion, a big anion like this, right? So obviously, like surrounding this smaller anion is easy rather than surrounding this big anion like this. And the second reason will be electronegativity, the charge, the amount of charge density I'm going to have on F minus is going to be higher than in the case of I minus, right? So again, I repeat, F minus is the one which is going to undergo more extensive hydrogen bonding, or let's say more extensive hydration, right, among these four because of two reasons. One is about the size. I would say a smaller anion can be crowded by the water molecules a little easier when compared to a bigger anion, in the sense that it is going to become more diffused layer, right? Okay. Second reason is about the charge density, right? So obviously you can see that all of them has -1, but a smaller anion with high amount of charge, with the same amount of charge, is definitely going to have more charge density, right? So more and more charge density, more and more with the hydrogen bonding. So you can see for two reasons that F minus is going to undergo more hydrogen bonding, more hydration is happening. Okay, now because of this, right? Now because of this, what do you think? Like, okay, I'll only give you the answer. Because of this, there is something which is going to happen. Which now what is going to happen is, since this F minus is maximum crowded, right? Now if it wants to go and attack the substrate, it is actually going to find it difficult, is it not? Because there's a sphere of water molecules surrounding this F minus, which will actually say resist F minus from going and attacking the substrate, right? So that way, what has happened to the nucleophilicity? Nucleophilicity is actually getting decreased, isn't it? So what you see is that the I minus is the one which is the least hydrated, right? So that will be the most free ion to go and attack the substrate, because it is not under any stress, it is not under any kind of resistance, right? So in this case, if you see people, the nucleophilicity order will be this way. I minus would have been a better nucleophile than Br minus, than Cl minus, than F minus. You see, it's exactly ulta of what we saw last time, is it not? But in this case, the reasons are different. The reasons here are going to be high, the extent of hydration, right? Now, how do you decide the extent of hydration? Based on size and charge density. By that, if I see F minus is the one which is having highest extent of hydration, so there the nucleophilicity is decreased to a maximum extent, whereas in I minus, nothing as of that happens. So it is going to be the best nucleophile in protic solvents. See, this is very important, people. This particular point I told you, I have seen even questions coming from this area in JEE exams also. Okay, so like but they will specify what kind. You should see what kind of solvent. If they don't tell you anything, right? If they don't mention any solvent, then you go for basic strength. But if they specify it's a protic solvent in water, something like that, if they specify, you have to take hydration into the picture also. Is it okay? Right? So now you can understand why is it that say Cl minus and OH minus, if I take, like, you obviously, sorry, you know so many reactions, right? You have Cl minus to be say OH minus. I know, like, the reaction happens, right? If I have RCl, if I put H2O, right, the reaction happens. Or say if I put NaOH, the reaction happens, right? Now why is it like this? Again, I can decide it based on the basic strength, right? So I have HCl would have been the acid here, and H2O would have been the acid here, right? So obviously I know HCl is a stronger acid, so definitely OH minus is a better base, or OH minus is a better base than Cl minus, even though if I don't look into it this way, right? So that is why this reaction happens. But what happens is, when I have ROH, right, and if I put water, or not water, if I put say any HCl, okay, if I put HCl, right, you do see that I have RCl coming, right? Now how this happens? This cannot happen, right? Because OH minus is a better nucleophile than Cl minus. That means Cl minus cannot replace OH minus, right? Now still, but this reaction, you should have seen this reaction in alcohol, ethers, and phenols. You should have seen this reaction, right? Now, how do you think it happens? Is it just that the Cl minus replaces OH minus? Is it as simple as that? If it as simple as that, according to my theory, I mean, not only to theory, according to whatever I studied, this is absolute wrong. But still, this happens. Any reasons? Anybody wants to come with reason? Okay, I'll give you a clue. The clue is mechanism. Same thing. Okay, one more clue also.
So both of them undergo cleavage, and then H and OH bond is easier to form.
H and OH bond easier to form? No, not like that. Say, I'll give you one more clue. I have NaC. If I put NaCl, right, this also has Cl minus, right? But this reaction doesn't happen. If I put HCl, this product comes out. But if I put NaCl, no product. There is no product. This is again a clue.
So hydrogen bonding, sir.
No. Okay, so I'll tell you, it's all about the mechanism, people. Now, what happens is, so from HCl, first the H plus comes. Okay, so this H plus is going to attack the lone pair on oxygen. Okay, so now what will happen if that happens? I will have ROH2 plus. Then what happens? I will have a removal of water molecule. Now this is a very unstable species, because water, if it comes out, is going to give me a more stable species, right? So if water comes out, I will be having R plus, and then the Cl minus comes. This is the mechanism. Okay, so what you're trying to do here is you are actually trying to convert OH minus, or say the alcohol, which is OH into a group which can be easily replaced by Cl minus, and that is actually water, right? I told you, always charged species, right, are always more nucleophilic than your uncharged species, isn't it? Right? So you are trying to convert this OH minus into a group which will be a good leaving group, so that again a Cl minus can come and attack. It is not like this is going to happen simultaneously. This comes here and this goes out. No, that is not happening simultaneously. Right? First the H plus attacks, I form ROH2 plus, remove water molecule, carbocation, then Cl minus attacks to form RCl. That's the reason. Okay, now there are a lot of stuffs like this, people. Actually, if you want to do nucleophilic substitution in any alcohol for that matter, right, it is actually pretty difficult. You want to convert alcohol, say, into an amine, or say how easy it is you do in case of your Cl minus, or say in your alkyl halides. You cannot do it that easily in the case of your alcohols. Nucleophilic substitution is not that feasible, right? But there are ways for you to make it more feasible, right? So the one of the reason is, one of the ways by which I can do it is this: when you convert OH into H2O, right, then it is possible. Now there are other ways of doing it also. There are something called as tosyl. Okay, I'll write it like this: TSCl, tosyl chloride it's called. I have TRCl, triphyl chloride. There is one more also, misyl. Yeah, MS, it is not ME. Missile. Okay, so what is this? Don't worry, like it's you don't have to worry about much. Right, so this tosyl is pretty simple. It's tosyl is toluene sulfonyl. So this is how the structure would be. So basically you have a CH3 toluene and a sulfonyl chloride, S one double bond O, another double bond O, and a chlorine. So this is what is, I would say it should be in para position, but still no issues, right? So this is what is toluene sulfonyl chloride, right? Now if it is going to be triphyl, it is trifluoromethyl. So trifluoromethyl, what happens instead of the CH3, I would have had a CF3, right? So anyways, you don't have to like, but this is very common, guys. This tosyl chloride is actually, you can even see questions coming from this in JEE mains. Okay, so anyways, this is not a big deal. So if I just TUTSCl, okay, so what is going to happen is, if I put this with alcohol, right, if I make it react with alcohol, what is going to happen is this, now I know alcohols are pretty acidic, isn't it? So this H plus and this Cl minus can leave. Okay, so how do I write this? Is I can write it as ROTS. TS is this group, tosyl group. Right now, this, guys, is a very, 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 very good leaving group. That means even if you put weakest of the nucleophile here, oh god, what is happening? Right, even if you put the weakest of the nucleophile here, I will have the reaction happening. Right, I will have the reaction happening. Now again, this is a way of converting OH into a better leaving group. Okay, so 99% you'll be, if at all you'll get only tosyl chlorides. But if really the examiner wants to dash your case, he can ask TS, I mean TR and MS also. Anyways, but 99% it will be tosyl chloride if they ask you questions from this. Okay, so the only reason why I use tosyl chloride is because I want to make alcohols undergo nucleophilic substitution. That's the main reason. Okay, now they can even use tosyl, not with chloride, tosyl acetates, right? So but the moment you see TS, you have to understand this will be used only with alcohols, especially for alcohols. Okay, right? So yeah, these are all about the nucleophilicities. Now the nucleophilic substitution reaction, yes, it is going to depend upon the nucleophilicity of the nucleophile, right? Now, but there is one more thing also. There is one more thing also actually, which matters for nucleophilic substitution. Maybe if I give you an example, I'll put this in the form of a question itself, right? Say I have RI, RBr, RCl, and RF, right? Now all of them, say I react with OH minus, right? So obviously all of them are going to give me alcohols. That is okay, right? So here the nucleophile is same, right? But you see the substrates are different. All the substrates are different here, isn't it? Now tell me, RI, RBr, RCl, RF, which will react faster? I mean, which will give me the product first? ROH. Tell me.
RI, sir.
Definitely, right? So it's pretty easy to understand. RI will give me the product first. Now, okay. Now, how do you go about it? Is because other than the nucleophilicity, you have one more criteria for deciding the nucleophilic substitution reaction. That is the leaving capacity. Right, the leaving capacity of the leaving group. Like obviously the leaving groups are I minus, Br minus, Cl minus, and F minus. In this case, nucleophile is OH minus, right? So leaving capacity of the leaving group. Now obviously more and more is the leaving capacity, right? Obviously more and more will be the would say the rate of the reaction, right? More and more is the leaving capacity of the leaving group. More and more will be the rate of the reaction, rate of the nucleophilic substitution reaction. Okay, now the next thing is, how do I decide the nucleophilicity? Sorry, how do I decide the leaving capacities? Right now, like nucleophilicity, we don't have so many complex, so many 5-point, 6-point criteria. We don't have. We just have one criteria for leaving capacity. Okay, so that criteria is my leaving capacity is inversely proportional to the basic strength of the leaving group. Okay, basic strength of the leaving group, right? So obviously now you can see F minus is a, oh wait, Inversely, correct, right? So higher basic strength means it is a very bad leaving group. That means I cannot have the nucleophilic interaction happening, right? But a weaker base, right, will be a good leaving group. So you can see F minus is the weakest base. Strongest base, right? So that will be a very bad leaving group. But I minus being the weakest base will be a very good leaving group. That is the reason why RI will give me the product faster. Okay, this alone you remember. Just stop. That's it. So leaving group, leaving capacity of the leaving group is directly, inversely proportional to the basic strength of the leaving group. That's what you need to understand. Okay. So other than this, I don't want to talk. I don't want to go into this SN1, SN2, all these, because you already studied, should have studied extensively about it. But if you have any specific doubts you want to ask, you can. Okay, you want to ask, you can ask. You want to ask me anything, guys, regarding SN1, SN2. Okay, now answer this question. In SN1, or okay, both in SN1 as well as SN2, the nucleophilicity of the incoming nucleophile matters. True or false? I'll repeat the question. In both SN1 as well as SN2, the nucleophilicity of the incoming nucleophile matters. That means it affects the rate of the reaction. True or false?
Also,
What did he say? Kana? I didn't hear. Someone said something now. False. Okay. Why you say it's false? Okay. Anybody else? Someone is asking me. Okay. There are no doubts. Fine. So yes, true or false, guys? The statement which I said. Both in SN1 as well as SN2, the nucleophilicity of the nucleophile affects the rate of the reaction. Or say, yeah, true or false? Okay, Aditi says true. Others? Okay, so someone said false. You want to give me a reason, Kanna? Why? Why is it like that?
so it depends upon the reactant. So still it can go.
No. Okay, the answer. Okay. Harini. Okay, why do you say it's true? Aditi and Sri Harini, both of you say it's true. Any reasons you want to come up with? Okay, no reasons. Fine. Okay, I will tell you the answer. The answer is false. And the statement which I said is not true. It's false. At least for that, you want to come up with reason. Why is it not true? Okay. Okay. I'm not sure why sir it wouldn't affect. Okay. Nice. Fine. Let me go to it then. Right. So guys, I think okay, in this page itself I can continue because it's nucleophilic substitution only. Okay. So when SN2, right, we know what does this 2 represents, right? This 2 represents going to be a bimolecular reaction. The order of the reaction is 2. Correct. So if I rate the rate of the reaction, the rate law equation, that would be some K, right, into the substrate. Say if it is going to be alkyl chloride, the alkyl chloride's concentration into the nucleophile's concentration. Correct? Right? So rate actually depends on the substrate as well as the nucleophile. Right? That's why we write it as 1 plus 1, 2, second order reaction. Right? Now, if it is going to be SN1, right, or the rate of the reaction will be K into what? This is first order, right? I cannot have both of them. Either one of them is going to come. Is it going to be the nucleophile or is it going to be the substrate? Concentration of what? Yes, substrate. You can be more confident in saying that you are right. Right. So you have RCl only here. Basically, the substrate. In this case, it's RCl. I just took an example, but in general, it is going to be the substrate. Oh gosh. Yeah. Right. So basically, what I'm trying to tell you is that in case of an SN1 reaction, the nucleophile, the nucleophile's concentration or the properties of the nucleophile doesn't matter. But in SN2, yes, it matters. Okay, because you see in SN2, the concentration of the nucleophile is included in the rate law. That means it affects the rate of the reaction, right? But in SN1, guys, you can see from the rate law, there is no role the nucleophile plays in regarding the rate. Yeah, the other aspects of the reaction, yes, definitely. But affecting the rate, no, it is really not going to affect the rate of the reaction. Either whether I have say a strong nucleophile or a weak nucleophile for SN1 reaction, it really doesn't matter. Okay, so I hope you understand how the statement is false. Nucleophiles' nucleophilicity is going to affect only SN2, not SN1. Right now, what about leaving capacity? Will it affect the rate of the reaction in both SN1 and SN2? Leaving capacity. Yeah, so I am telling, I think you are answering that question. What comes there? Okay, so I'm asking, what about leaving capacity? Will it affect the rate in SN1 as well as SN2? Yes or no? You can just type yes or no, or unmute yourself and say yes or no. Only in SN2, I think so. Okay. Anybody else wants to give me an answer? What do you mean by no? That means they're telling that leaving capacity will not affect.
Yes, sir.
Okay, fine. So now tell me, leaving capacity is about what? Is it not about the substrate, guys? In substrate only I have the leaving group. Is it not? Right? So obviously what you see here in both SN1 as well as in SN2, the substrate is there. That means obviously in both the substrates, I have the leaving groups, right? So leaving capacity does matter for both SN1 as well as SN2. But nucleophilicity, no, nucleophilicity matters only in SN2. SN1, it doesn't matter. But the leaving capacity of the leaving group matters both in SN1 as well as SN2. Because you see the substrate here, the substrate concentration is included in both of them, isn't it? Right? So if you just think about it logically, I think you'll be able to understand. I think you're overthinking. Like you are trying to come up with some big reasons, but the reasons are not that big, people. Like if you just look into it and think logically, not much. Right? So hope you understand why leaving capacity matters for both SN1 and SN2, but nucleophilicity matters only for SN2, not for SN1. Is that okay? Right? Fine. Now moving on. Right? Now we know about SN1 and SN2. We have studied a little bit, right? Like hope you understand SN1. I have a two-step process. A carbocation is formed. A racemic mixture is going to get formed, right? And in case of SN2, I have a single-step process. I'm going to have inversion of configuration happening, right? Okay, so all these are the and again in the case of reactivity, in case of SN2, primary will be more reactive than secondary, secondary will be more reactive than tertiary. Sorry, yeah. So that the reason there is bulkiness, right? Now in case of SN1, tertiary is going to react faster than secondary than primary. There it is because of stability of carbocation, right? Okay, fine. Now other than S1 and SN1 and SN2, guys, there is one more mechanism which is proposed. Okay, now that mechanism is proposed for benzene ring substituents. Now, generally, what happens is when you have, say, this one, right, benzyl chloride, if I put, say, NaOH in this, right, generally this reaction I can make it happen. I can make it happen if you go for really high temperatures, 623 degrees Celsius, 300 atmospheric pressure, very extreme conditions. Like this is actually, this is a name reaction. This reaction is called Dow's process or Dow's reaction, right? So what will you see is that I'm going to have the nucleophilic substitution OH, right? This would have been happening. Okay, so we have to come up with a mechanism for this. It is neither going to follow SN1 nor going to follow SN2, right? Now, how do I come up with a mechanism for this, right? Now, the mechanism proposed is what is called as a benzene mechanism. Okay, the intermediate, the benzene is actually an intermediate, just like your carbocations, carbanion, something like that. Benzene is actually an intermediate. Okay, so let me look into the mechanism, like then you'll understand. Okay, we'll move on. Wait, am I doing it? Yeah, I'm doing it correctly. Yes. So first, what happens is, guys, okay, now let me put the bonds properly. One, oh, oh God. Okay, benzene, let's say a chlorine. Okay, right. Say in this case, I'm going to use, like, OH minus is also a base, right? Like you can use any other nucleophile also. Say there are something like KNH2, right? So KNH2 is going to give me the nucleophile as NH2 minus. So that also you can, again, that is a base. NH2 minus is going to act as a base. Anyways, there's a H here, hydrogen. It is a hydrogen here. Say now I put this NH2 minus or OH minus, doesn't matter. Okay, now what is it going to do is that this NH2 minus is actually going to take this H plus first. Okay, this NH2 minus is going to take the H plus first. Okay, now what will happen after that? So you will see that there'll be a negative charge here. Is it not? H plus has left, right? So I still, other things are still there, Cl and 3 more bonds. Right, now next what is going to happen is this negative charge, obviously there are 2 electrons here, you can understand that. So this is going to make a bond and Cl minus leaves. Okay, again, I hope you understand, right? I have a negative charge that is going to make a bond and this one leaves, Cl minus leaves, right? So what will you end up with now? You will end up me and my bloody stylus. Okay. Right, so you will have a triple bond. Right, now this is what is called as benzene, people. Right, this is what is called as benzene. Okay, a triple bond, a benzene ring with one extra bond, I mean, rather than double bond, I'm going to have a triple bond. This is what is called as benzene. This is an intermediate. So hope you understand how it forms. First, the H plus is removed, forms a negative charge, and that negative charge forms the bond, by that eliminating the Cl minus. Okay, right, next. What is now the nucleophile is going to come. NH2 minus is going to come. Okay. Now, obviously, now it can attack in two sides. Either say it can attack here or it can attack here. Wherever the triple bond carbon, either of the two carbon atoms, wherever you want, you can attack. Say, let me take this one only, right? The second one, this one, I'm going to take. Okay. So let me see what's going to happen. Okay, so now I have a double bond, double bond, double bond. Now the NH2 would have attacked here. Right, no issues. Now obviously if this attacks here, this bond would have gone here. Let me actually rub this part so that you will not get confused. Okay, right, now what happens now if this attacks here, this bond would have gone here. Okay, this bond would have gone here. So obviously what will happen, there would have been a negative charge on this. Correct, right? Now what will happen, you have removed H plus, just add the H plus to this negative charge. So you will be coming back with benzene ring with an NH2. Okay, now you can ask me, sir, the Cl was here, the NH2 is here. It all depends on where it attacks. If it would have attacked here, right, this place, then I would have got the same exact product. But you don't have to worry about it. Since this is symmetrical, you really don't have to worry about it. Okay, so it's pretty simple, guys. First, the H plus is removed, form a negative charge, and then make the triple bond, form the benzene, remove the H, remove the Cl minus, and then make the nucleophile attack. If the nucleophile attacks, again the bond breaks, makes a negative charge, and add the H plus, the nucleophilic substitution reaction is done. Okay, right. Now this is what is called as benzene mechanism. But very rare. Like again, this is not going to happen so easily as you think it is, because this benzene is going to be one of the most unstable species I can have. But again, I do a course. I have a subject called as physical organic chemistry. Okay, so I have some time. Fine. So physical organic chemistry, what I do is I study about how do you predict the mechanisms. Now you see all these mechanisms are already known to you that I'm teaching you, right? But in my course, in my college, what I do is there are ways by which you will be able to predict what will be the mechanism. Okay, and there are experiments also you will be able to do. Sometimes you will be able to trap a carbocation, visualize it, but again for a very short period of time. But still all these things are possible. But benzene is purely theoretical. Okay, now there is no experiment where benzene has been isolated and studied, no. But still it gives me a reaction path, right? It tells me, okay, this explains that, okay, this is how the product is formed, right? So it is accepted. Not only this reaction, so many reactions, this mechanism is just proposed theoretically by scientists. Obviously you cannot just violate the laws of chemistry and give a law, give a mechanism. That is impossible. But still, but all the theoretical aspects which maybe if you study MSc chemistry, right, maybe at that time you will know that there'll be a subject called a beautiful subject. I love the subject, right? A beautiful paper actually, right? So you will also know what are the ways by which I'll be able to predict the mechanism of a particular reaction. Okay, fine. So that's about the benzene mechanism, but I want to give you a problem. Now the problem is, if I have an NH2, obviously NH2 cannot be replaced, guys. Do not even think about it. I have a Cl and I go for KNH2, right? Now what I see is this is one product, right? And there is another product. Okay, And what I find is this is the major product. Okay, and this is the minor product. This is a minor product, and this is the major product. I wanted to come up with a reason for this, and you can come up with the reason on and only if you go for the mechanism. Now, get your paper, get your pen, draw the pen. Now, draw the mechanism which I taught you here, right? And if you draw the mechanism and see, there are details inside, which is going to tell you why this is the major product and not the other one. Go for it. I'll give you 2 minutes time.
Sir, because in the first compound there's steric hindrance between the NH2 and NH2.
Steric in, no, that's not the reason. No. Okay, let me keep the mechanism for this if you want. Okay, this is the mechanism.
Sir, is it because after we break the triple bond in
Mm,
the benzyne
mm,
thing,
mm,
uh,
mm.
we get the lone pair in ortho position rather than the meta position, so that
Okay,
resonance
I mean,
occurs.
not the lone pair, it is the negative charge. Okay, so negative charge
Yeah,
in ortho position than in the meta position. Why? Yeah,
so that it can
and
undergo resonance and it will be more stable.
okay, yes. Resonance, no, but more stable, yes. Correct. Your answer is 90% correct, Kana. Good attempt, right? So we'll see what happens, right? So guys, you are seeing the mechanism, the same thing. Say, I'll just like if I can just put an NH2 here, like I can save some time, right? Once again. So let me put an NH2. Okay, all the places. Okay. Now, guys, till this point, no problem. Benzene is formed. Okay. Now, when the nucleophile attacks, right? Now you can see, as I told you, there can be two positions of the nucleophile attacking, either this carbon, right, or this carbon, a triple bond carbon. Right now, if you say now, if I go by the existing one, say this mechanism, if you're going to attack this carbon atom only, where will you form the negative charge? The negative charge is formed here. Correct. Now you see that negative charge is in between two two electron withdrawing groups. Is it not? Or I actually the answer here is correct. Kana. Resonance is also possible. Okay, resonance is actually possible. Yes, but resonance, even if I have it here, actually resonance is possible. You can see this bond can come here and this can break. Again, if the negative charge would have been formed here, this would have come here and this would have been broken. Right, but resonance is not the resonance is happening in both sides. Right, but more importantly, what is dominating here is, guys, 1 second. Okay, yeah. So what I was telling, yeah. So it's all about the negative charge. You see, the negative charge is in between your two electron withdrawing groups. That means this carbanion which is getting formed is little stable when I compare it to, if I can draw the other structure. So I had an NH2. right? Now where would have been the another NH2? If this would have been here, NH2 would have been here, right? I mean, I should not put a. So there was a double bond, a double bond, a double bond. The negative charge would have been here after breaking the benzene ring. This one. So basically, now the NH2 attacks this carbon atom, so that it will end up with this. Right now, where do you see? Now it is not in between two electron withdrawing groups. It is just one carbon atom away from an electron withdrawing group. Right. So comparing this and this one, right? Definitely, this is a more stable carbon ion when compared to this one, right? So that is the reason why you see this as the major product. Okay, right? Pretty easy. It's all about the stability of the carbanion. After till you form benzene, no problem, right? But benzene, I know I can have two sites of attack for the nucleophile, right? So now depending on whether the attack happens and where is the negative charge formed, whether it's stable or not, again the products can be different. The major and minor products will be there definitely. Is it okay? Right? I hope everybody understood why this is the major product. Because you see the negative charge would have been formed here, that would have been more stabilized by these two, NH2 and NH2, electron withdrawing groups. Okay, what is the time? 8:27. Okay, guys, I think I have to stop today. There is just one more thing left. There is electrophilic substitution. Okay, we saw so many reactions. I really don't know how to come up with the problems for this. But see, I will sort out something, right? But again, we will do a couple of, we'll do a good number of problems for all the reactions which we saw. Okay, right? But the last thing would be electrophilic substitution. Electrophilic substitution would be happening only in benzene rings, nitration, sulfonation, so tosylation, all these things. Okay, sulfonation, chlorination, Friedel graphs. Okay, so all these things we'll see next class, and I think we'll wind up. Okay, right? So now what I really want to do is I don't want to do the problems now. In the sense that you're still like I'm obviously not going to teach you every reaction you have seen in your organic chemistry 12th, right? But I will teach you certain important reactions like aldol condensation, right? Reimer-Tiemann reaction, and some other important name reactions are there, right? And those things I'll teach you. We saw majority of the reactions, guys. This makes up for at least 60 to 70% of reactions which we see in organ, at least for your level. Right, this is done. Right, other than that, I can the nucleophilic itself, I can have say Williamson synthesis, Wood's reaction. So all these, the name reactions we will see in a bit, right? With some touch we'll do, right? Other than that, we are okay. Aldol condensation, that is very important. What else? Any other? There is Hoffman rearrangement, Hoffman elimination. Oh, when I talk about elimination, I didn't speak about that. Okay, there is one more type of elimination also. Right, other than E1, E2, there is something called as Hoffman elimination that also we'll see. Other than that, there are various name reactions. Okay, so all these things will try to, maybe I will be requiring some 3 to 4 hours for me to complete that, and then overall we'll try to do some problems. Or I don't know, like this is what I feel is good. What do you feel, Kanna? Like, do you want to do problems right away after this? What, just after completion of electrophilic substitutions, or you want to do it at the end?
I think we'll do problems after this.
We'll do problems now only.
Yes, sir.
Yes, sir.
Okay, fine, cool then. So maybe I'll go with your choice. After finishing electrophilic substitutions, maybe I will take 1 or 2 classes. Not 2 classes will be too much. 1 class, maybe a 2 hours class we can have. That will be good, right? Maybe on a Sunday, right? Maybe if you can have a 2 hours or even 3 hours, if you're okay, I can do good number of problems. Okay, so that we'll do, and then I'll take up equilibrium. Okay, again, we'll go for physical chemistry. Okay, so fine, guys. Thank you so much. That's it for today. Any other questions if you have, you can ask.
Thank you, sir.
Right. Okay, there are no doubts. Okay, people. Thank you so much. We'll
Thank
see
you, sir.
tomorrow.
Thank you, sir.
Thank you.
Thank you.